This is just going to be a brief introduction to Section 5.2. We won't get very far into 5.2, but we're going to be working with special right triangles. If you remember from geometry, they were called 45, 45, 90, and 30, 60, 90 triangles. And a lot of the calculations and just common facts that we come across throughout the entire trigonometry course are going to hinge on those two triangles, okay? So we're going to become very used to those and very kind of in tune with them. If we don't know these triangles right now, or we may left geometry not having a great grasp on them, that should and needs to change soon because they're vital to this course. First thing is I'm talking about a 45, 45, 90. A couple different ways that we can talk about it. Okay, we call it 45, 45, 90. We can call it a right isosceles. Okay, so those are kind of synonyms. And if we really want to get into it, this is pi over 4, pi over 4, pi over 2. I don't know how often you would see that, but 45 degrees, if we go off of what we've talked about in the last couple of days, changing that using this conversion factor, 45 degrees, those are going to cancel. It's going to be pi over 4 radians. And then if I double 45, I'll get 90, so double this, and I should get pi over 2. So working with a 45, 45, 90, or right isosceles triangle, we note those two sides are the same length. So if we call this one n and that one n, and I want to come up with the length here of C, I'm going to use this formula, Pythagorean theorem, where A and B are your legs. So A is going to be our n, B is also n, and then C is the hypotenuse, so C squared. So that's going to give me 2n squared is equal to C squared. Square root both sides, so I'd get square root of 2n squared is equal to C. And now if I break those apart, radical 2 and radical n squared, the radical n squared will leave me just n. So I get n radical 2 is equal to C. And hopefully that's something that you guys remember from geometry, if it's a 45, 49, 45, 90 right triangle. And what does that allow us to do? Well, it allows us to say, well, if this side is 5 and that's 5, then the hypotenuse automatically is to be 5 radical 2. It also allows us to do something like this, where we say if this is 7 radical 2, we automatically know then that the legs are both 7. It also allows us to do something like this. It's a little bit more involved. Let's say this is 13. Okay, well, if I go back up to this one, the way I went from, well, let's start with this one. If I started with these, the way I went to get the hypotenuse is I multiplied a leg by radical 2. Here, if I start with the hypotenuse, to get a leg, you're going to undo the multiplication you did here. So undoing multiplication will divide by radical 2. Same thing happens here. I'll divide by radical 2 to get the leg. So it'll be 13 over root 2. 13 over root 2. Now we don't like the roots there, so we'll rationalize it. It gives us 13 root 2 over 2. And that would be the length of a leg. So that's all the stuff that we've done with 45, 45, 90 right triangles. The other special right triangle is a 30, 60, 90. So demonstrate the information that we know about a 30, 60, 90. So in a 30, 60, 90, the way we derive the formula for that is we're going to start with this triangle here, and we're going to construct it this way. So if I construct that triangle, that's called obviously an equilateral triangle. Okay, we have a corollary in geometry that says in equilateral triangles, or in all equilateral triangles, they are also equal angular. So equilateral implies equiangular. Okay, and that's only for triangles. Okay, so like an equilateral quadrilateral does not mean it's equiangular. An equiangular quadrilateral does not mean it's equilateral. Okay, but for triangles, one implies the other. So if that's true, then that makes this 60 degrees, 60 degrees, 60 degrees. Okay. Now I don't know the side lengths here, but I do know that they're all the same. So let's just call them all n. Now we also had probably one of the most prevalent theorems in geometry said in an isosceles triangle, if we look at the vertex angle, so the vertex angle in an isosceles triangle is the angle that is formed by the two congruent legs. So an equilateral triangle is isosceles. So if I look at two congruent legs, we're just going to use the left and the right here, this would be considered a vertex angle. We had a theorem that said if you find the angle bisector of the vertex angle, so that segment right there, okay, we know it should exist because every angle has a bisector. So we're going to say we're going to find that angle bisector. That's going to make this angle 30 degrees. Okay. If I continue dropping that down, okay, what we found out in geometry is that the angle bisector of the vertex angle is the perpendicular bisector of the base of the isosceles triangle. And the base of an isosceles triangle is always opposite the vertex angle. So if we do that, my hope is you can see here what we've generated is this triangle here. Okay, what kind of triangle is that? It's a 30, 60, 90. Okay, so yellow triangle is a 30, 60, 90. If we think about it in terms of radians, 30 is pi over 6, 60 is pi over 3, 90 is pi over 2. Again, probably not going to see it written that way very often, but that is the case. Okay, so going off of our geometric concepts, that if this angle bisector here is the perpendicular bisector of the base, meaning that if this entire base was n, then this distance here is n over 2, or half n. Now, I don't know what this length of this leg of the yellow triangle is, but I now have two sides of this yellow triangle. And this yellow triangle is a right triangle. So right now, I'm going to call this A because I don't know it. But we would have the ability to say that A squared plus then this side here, which is n over 2 squared, should equal this side, which is n squared. Now to find this length here, what I'm going to try to do is just solve for A. So solving for A, I would have A squared. I'm going to go n squared over 4 here. And this will be n squared there. Isolate A squared, so I'll have n squared minus n squared over 4. Now, if I want to combine these like terms here, I'm going to actually make this 4n squared over 4. I'm left with an a squared equals 4n squared minus 1n squared is 3n squared over 4. Square root both sides to get a. Okay, so when I square root both sides, I can put the top in its own radical, put the bottom in its own radical. So I get radical 3 up top. The n came out, so radical n squared I'll take square root of it, just gives you n, and then I have 2 on the bottom. Okay, so a ends up being n radical 3 over 2. Okay, then what we do, if we look at this yellow triangle right now, what we have is n radical 3 over 2. We have n, and we have n over 2. And this would be the 60-degree angle, and this would be the 30-degree angle. Okay. We don't like those fractions, and basically what we can do, because of dilations that we talked about in geometry, we can actually double every side length and still have a 30, 60, 90 triangle. So if I double every side length, this is going to give me, basically, that's going to just go to n radical 3. This is just going to go to n, and this doubled would give me 2n, and that just gets rid of my fractions. And that becomes the basis for all of our 30, 60, 90 triangles and their lengths, their side lengths. So if we have a triangle where, if that's 30, 90, and this is 60, if I tell you that across from 30 is a length of 1, then across from 60 is a length of radical 3, which I believe is about 1.7. You can double check me on that. And then across from here would be 2. And that should make sense, because across from the smallest angle should be the smallest side. So if we put these in order, smallest angle, middle angle, largest angle, then we should have smallest side, middle side, biggest side. Okay, and those are all facts that we learned about inequalities in all triangles and geometry. Okay, but this allows us to do a lot of different things here, like we do with the 45, 45, 90. If I start with this side here, which is 3, okay, so that's across from 30, so that was my n. Then if I double that, I should get that side. And if I multiply it by radical 3, I should get that side. Or if we start with, let's say we start here with 8. So 8 is the 2n side now. So n should be 4. That goes across from 30. And across from 60 should be 4 radical 3. All right, so that's just a reminder or an introduction of these special right triangles, but they're going to be very important to us as we move through these first 2 chapters, and then after these first 2 chapters, they should be just inherent. You should know them, because we're going to use them so often. And you can kind of see over here the common theta that we use in degrees. The common thetas that we use are all, for the most part, from those special right triangles. And even, right, this we're going to see like 120. We'll see like 150, 210. Those are all multiples of 30, 60, and 45. Okay, so those become very useful to us. And these values over here that we're going to see and we'll just do one, and then we'll talk about the rest of these in the next video. I think we're kind of running short on time. Yeah. If we talk about sine, okay, and we talk about this, and I'll have a much more detailed explanation of these trigonometric ratios with a GeoGebra applet in the next couple of days in regards to like similarity and stuff like that. But we talked in geometry that sine from SOHCAHTOA is opposite over hypotenuse. Okay, so let's say that we're working in a, let's say 30, 60, 90 triangle, and let's say that this 30 is our theta. Okay, if this side here is n and this is 2n, okay, so across from 30, this side here would be our opposite. And you can use n, you can use If you want it to be 4 and this be 8, you want this to be 12 and 24, you want 1.5 and 3, pi and 2 pi. It doesn't matter what that number is, because the relationship is that that's going to always be double it. So that's the opposite side, and this is the hypotenuse. Okay, so if I say sine of theta in this case, and our theta was 30 degrees. Okay, sine of theta is opposite over hypotenuse. Remember, opposite, which is the length of n, divided by a hypotenuse, which is 2n. The n's cancel out, and it leaves me with 1/2. So what we see here is that the sine of 30 is equal to 1/2. Now, like I said, it doesn't matter if that was n or 2n. Let's do this as, if this is 15, then this would have been 30. So then instead of n over 2n, you would have had 15 over 30. And what's 15 over 30 reduced to? Still the 1/2 that we had right there. Okay, so what does that mean? Sine of 30, no matter what, if I've got a 30, 60, and the sine, cosine, tangent, those are relationships for right triangles and right triangles only. So when I see sine, I know I'm talking about a right triangle. And they say sine of 30, then I know that the opposite divided by hypotenuse ratio is always going to be 1 over 2. And that's what you're seeing down here in this table when it says 30, sine of 30 is 1/2. Okay, if we take our calculators out, we can just gotta make sure I'm in the right mode. I'm gonna use degrees, so I need to go down, hit mode, go down to degree, hit enter, and now I can just hit sine of 30, and our calculator is gonna know that it's programmed to divide opposite of hypotenuse over any 30, 60, 90 triangle. It's always gonna reduce to 1/2. If I was in radians, in this case, to get that 1/2, you need to know that 30 degrees is the same thing as pi over 6.5. Okay. So that's where these values are going to be coming from. Again, I'm going to talk about this in the next video, but this table is here. But if you memorize that table, I think you're wasting your time. Okay, because if you can remember SOHCAHTOA and these special right triangles, these hopefully these are things that like the back of your hand, or within the next couple of days you know them like by the back of your hand, so that if you're in a pinch and you need this chart or you need to create this table, you simply just grab that information from these 30, 60, 90 triangles, 45, 45, 90 triangles, and fill your chart in that way. So I guess what I'm saying is this chart is created or compiled using the knowledge from 30, 60, 90, 45, 45, 90s, and that table right there, which we'll talk about in more detail in the next video.